With the first part of driven piles out of the way, or the section on exclusively on driven piles out of the way, we can turn to two topics, one of which is a different type of foundation, but another is kind of a transition between one and the other. And that is lateral loading of piles. And then from there, we'll proceed to drill shafts and auger cast piles. In the very early stages of deep foundations, and we talked about driven piles, we talked about why we have driven piles to start with. A major reason why we have any deep foundation, or either driven piles, deep foundations, or whatever, is lateral loading. Lateral loading, as we have seen, is not, generally speaking, the forte of shallow foundations. There are ways in which we can assist shallow foundations in withstanding lateral loading, but ultimately, if lateral loading is serious enough, we require a deep foundation. And there are several sources from lateral loading that we have to consider. One of them is river current, both in terms of just the sheer lateral loading and the fact that the current frequently erodes material around the deep foundation or around the foundation and makes it subject to scour, where it actually degrades it. Now, in the case of a shallow foundation, that can be catastrophic fairly quickly. In the case of a deep foundation, if it's deep enough, it will withstand it. Ocean wave forces, we see this for offshore platforms and offshore wind farms and that sort of thing. Slope movements, laterally low, we talked about these in soil mechanics. Cable forces on transmission towers, but also the wind loads on the transmission tower, period. Earth pressures on retaining walls is a form of lateral loading. And in fact, there are commonalities between this part of the course and what we looked at with in retaining walls, especially with sheet piling. Wind loads, seismic loads, I talked about those earlier in seismic retrofits. Impact loads from ships, we've talked about those as well, and eccentric loads on columns, which produce column buckling. Lateral loading in piles is different from axial in that instead of the pile acting as an axial member, it acts as a beam in lateral support, very similar to the way in which we saw with sheet piling particularly, because we didn't really get into much into lateral beam action and other retaining walls. And basically, those loads at the pile head can either be horizontal or a mixture, actually. You can have both lateral and axial loads at the same, but let's stick with the lateral. If we're sticking lateral, we're talking about a horizontal load on a pile head. And also, the pile can have a head moment. We're going to talk about how that's generated in a little bit. And then, as you go down, any beam reacts as beams do in bending. The difference is, as was the case with sheet piling, instead of having a bunch of nice little rigid supports, you have a continuum of plastic material which is resisting the load. And that's what makes it complicated. And the amount that obviously you would expect a pile to deflect more at the head than further down, it does. And it was, and so therefore that's how a pile resists lateral loading. The loading is at the head of the pile and the resistance is below that, as opposed to so as a sheet piling is kind of the opposite, where the loading is at all along them, and the resistance is is split between an anchored wall between the passive forces down here and the anchor up here. So there are important differences, but there are important similarities as well. Battered piles represent I've talked about them before, are basically an angled pile. Any pile, mostly, and this is mostly with driven piles, you don't see many drill piles driven at an angle. Most is mostly with driven piles, and basically the idea is if you put the pile at an angle and you subject it to a horizontal load, then that load will have a horizontal and vertical component, and it will shift the loading in the pile over to some, it gives some resistance to, it turns a lateral load into an axial load and gets rid of the beam effects, at least to some degree. For many years, this was the method of dealing with lateral loads in piles. And you see them on bridges. You see quite on bridges and that sort of thing. The problem with batter piles, well, there are two reasons. One of them is they can be a bear to install. I've been involved in many projects where batter piles are just, sometimes the batters are severe, reaching 1 to 1, and 2 to 1 or 1 to 2, depending you express that, or 3 to 1, and you've got it, and to install to get the equipment to install these can be a nightmare in some cases. The other problem is that batter piles tend to withstand lateral loads in a very stiff fashion. In other words, without a lot of deflection. In some cases, that's fine. In some situations, particularly in seismic, that can be a real first-class disaster because the stiffness of the system will lead to catastrophic failure if whatever lateral loading happens overwhelms the system. Our analytic methods. Traditionally, foundation courses have concentrated on the shorter ones. I concentrate on the longer ones. In short foundations, you have a situation where the pile can be considered as rigid, and the pile basically acts as a rigid rod, and you can ignore any effects of the pile itself on the system. And that's probably the best known method to deal with that is Brahms' method, after Bengt Brahms, who was a Swedish geotech, and some of the little drawings, I think that one is one of them, actually came from Bengt Brahms. For longer foundations, you get a situation where you cannot ignore the flexibility of the pile, and as a result, you have beam-like action. And you almost inevitably to do that. When they first discovered that this was an issue, they tried to use linear methods like Winkler methods. It quickly became apparent that Winkler methods weren't going to cut it. They were just too they just could not. The pile was okay with it. It was the soil that could not be modeled with Winkler methods or any other kind of linear methods. So we had to turn to nonlinear methods, and ultimately from a math standpoint, to numerical methods, either FEA or finite difference, like your PY curve methods, to solve this problem. Basically, when you and part of the nonlinearity, of course, is the soil. It's always, soils are nonlinear. Some of it, though, is due to the nature of the soil. If you had, for example, you've got a slice of soil. Just take a slice at any point along here. And by the way, whether you use a rigid method or a flexible method for the pile, no matter which one you pick, the deflection of the soil from the rest position is always changing as you go down the pile. Always in lateral loaded piles. There's no way. It's just not going to happen that a pile is going to move in move horizontally and stay vertical in a situation like that. When there is before loading, you have a nice even pressure distribution. You have your horizontal pressures, which are generated by your vertical pressures, and around loading. As you push the pile, what happens to you is that you compress the soil on this side, in the direction the pile is moving, and the soil expands to some degree, or actually in certain cases it will actually break away from the pile. In that only adds to the complexity of the response of the pile, and that changes as you go down. And then on top of that, not only does it change with the deflection, it also changes with the soil type and the consistency of the soil. All of these things are going to add up to a complicated situation. For the soils part, we develop a system of things called PY curves. And the whole effort to get a numerical method that was reasonably reliable for predicting is primarily the work of two people. And one of them is Lyman Reese. Both have passed on. He taught at the University of Texas for many years, and much of his work and the work of his colleague and others was either sponsored by the Corps of Engineers. In fact, some of that goes back to the 1970s when the Corps started to first get interested in this. And some of the original monographs and the code are actually available on my website. And it started with the PY curve. You know, he was a very well respected, and I've heard him speak. And Lyman Reese was a significant pioneer in this field. This became almost his signature accomplishment. But the other person that was involved with him was Mike O'Neill, who taught at the University of Houston for many years, and I was privileged to count him as a friend. I think one of the great losses this industry has withstood is his untimely death. Was in about the middle of the first decade of the millennium when he passed away. I have his memorial somewhere on my website as well. Mike was a fine person and a very, very good geotechnical engineer and academic. And the two of them together with others came up with these PY curves. And basically what these PY curves do is for a given segment, pile size, whatever, they give you the deflection, the force deflection or pressure deflection characteristics. And and if you throw those into a numerical model, which they used to find a difference model, they determined they would actually be able to estimate the response of the pile or the soil, the response of the soil in conjunction with the pile to its lateral loading. When they obtained their data from their empirical tests, they applied these to the model, and of course the pile was suitably instrumented, and then they developed the PY curves from that. There had been some attempts to develop non-dimensional methods. These have achieved some degree of success. They're not the easiest things to use, but they were for a while about all we had until the PY curve programs were up and running. And today they're fairly common. There are, L-Pile is probably the best known descendant of Reese and O'Neill's efforts with COM 624, which is what they called the program they developed for the government originally. And so there are other numerical methods. There's a whole list of numerical methods which have been used with, and actually, and I'm going to come back to this, Arcadis a few years ago did an interesting study, and it's on my website, about the accuracy of different lateral loading techniques, be they non-dimensional or whatever. So it's an interesting subject, how it's developed. One thing that every lateral loading routine has to deal with is the issue of infixity. Because, you think about, well, we have a pile, we apply a lateral load at the top, it responds, we live happily, we figure it out, live happily ever after. No, not quite, because how it responds depends on its infixity. And I don't know how far you've got into beam theory, but basically there are 3 degrees of freedom for every constraint point for a beam. The beam can move in the direction of basically the beam's axis, along the beam's axis. It can move perpendicular to that axis, and normally refer to these as, if we have a beam laid this way, we refer in the X direction and the Y direction, and then it can also rotate around that axis. And we can constrain beams in different ways, and will produce different responses from the beam. For example, a simply supported beam, in order to be simply supported and statically determinate, can have, I'm just going to assume this, we're talking about a horizontal beam because I know I'm sitting here looking at a vertical one. So you've got at each individual point, as long as the 2 points can rotate in both ways, and we constrain any movement in this direction, and we only on one do we constrain movement in this direction. If we constrain movement in the x-axis in both directions, we will no longer have a simply supported beam. So those 3, and of course there are also other kinds in addition to that. In addition to, say, for example, we allow a beam to rotate, we could have where if it rotates, it produces a certain torque that resists that rotation. Or if we have a X or a Y deflection, we have a spring of some kind that, even though it can deflect, the force is dependent upon how much it deflects. So we have all kinds of combinations. In the case of laterally loaded piles, we're mostly interested in 2, but we also actually have 3. One of them is the pile head is free. Basically, the pile head is free in all directions. In other words, it can go horizontally, it can move. It could move vertically, obviously for axial loads, and it can also rotate. Completely free to rotate. It has the freedom to rotate. So that's a free head. And although there are, we would normally associate a free head with something like an offshore wind farm, there are other conditions which can be said to simulate a free head. We also have the fixed head. Now, the fixed head does not mean that the head is not able to move at all. It can actually move in this direction perfectly. It can also, but it cannot rotate. It cannot rotate. In other words, the theta up here at the top is always 0. There's no angle of rotation allowed, and that's what these rollers are all about. It's also possible to have it where you have, say, like a spring, a torsional spring acting at the top, where the beam does not rotate. We're not going to worry about those, but obviously those are significant for certain types of structures. We're going to, these 2 are the ones, this is the free head and the fixed head. That's the distinction between the 2. Now, in presenting a method for use in class, we could look at different types there are different ways of doing this. Some people just throw up their hands and say, well, this is really, let's just use Brahms' method. Let's just forget about piles that are not rigid. Particularly with seismic, the flexibility of the pile is the whole point of using a laterally loaded. So I'm not sure. I think I would, if I had to throw one out, I'd rather throw the rigid one out than to throw the flexible one out. And in fact, it's easier. The COM624G program is available on vulcanhammer.net as a DOS program. And I actually have a piece somewhere on DOS programs, on how to use DOS programs. Most students today do not want to fool with DOS programs, even though many of them are still useful. One of the trends we've seen in engineering software is the increasing scarcity of free engineering software other than spreadsheets. Now spreadsheets are a different story, and we're actually going to use one, but we see more and more engineering software, particularly in the early years, I mean by the 1980s and early 90s, we had a fair amount of free software out there. The government had developed it at its expense. It was public domain. People could use it. The transition to Windows made it harder for engineers to develop the software without a lot of help from other people. And as a result, we had that, the government still developed some Windows software. It's gotten to the point where virtually with a few exceptions, and there are certain types of software with student versions and whatnot, but with most engineering software we have, particularly in this field, most engineering software is proprietary, and a lot of it's expensive. And also, there's a learning curve, and we have many topics to cover in this course. And to expect everybody to stop for a week and figure out how to use the software is probably asking too much, and it really obscures what we're trying to accomplish. So what I am presenting to you is something called the characteristic load method. CLM was developed at Virginia Tech probably in the late 90s, early 2000s. It's been refined some. And it basically what they did with CLM is they took the COM624G programs and they ran a lot of them, and they're for different cases. And they ended up running a lot of them, non-dimensionalizing the results, and then they turned around and they put them in a set of equations and charts, which you could use to determine what the different parameters of the pile are. It's very simple and quick, particularly if you have the spreadsheet armed with a spreadsheet that which I furnish you on my website to actually compute this. It assumes there's a constant EI for the depth of the pile, and it assumes the foundation is long enough to be considered fixed at the toe. The long foundations criteria. When I first started teaching this course, I taught the hand solutions, and we had all kinds of problems. The CLM spreadsheet is the most general application of it, and the Tanwave program actually has an implementation of CLM2, which actually CLM2 is the CLM1, where they made the improvements and put it in the spreadsheet. The CLM method, to be real honest with you, is very simple. It's a good way of illustrating what's going on. It has many limitations, and as a result of that, in the Arcadis shootout, so to speak, it did not come out very well. It's good for educational purposes, and it's good for very limited purposes for getting some preliminary numbers and checking some things when you're not really well flush with information, I would not use it for anything beyond either one of those applications. It makes for an interesting. It gets us up to speed more quickly than just about any other method, but the CLM method has too many limitations, in my opinion, to be used on a regular, ongoing basis if designing lateral loaded piles is what you're, part of your living. It also includes, the CLM2 also includes group effects. There are group effects because if you load a pile, you remember a couple of slides back, or 3 slides back, or 4 maybe, you remember this effect. Well, if this effect is big enough, if you've got enough big enough effect, if there's a pile there, it's going to affect that, and these two deformed fields are going to intersect. And so therefore there are group effects in laterally loaded piles. These are the characteristic load and moment equations. There's a little handout about on in your with the CLM2 spreadsheet about how they work. But I'm going to go straight to you can see that these are fairly complicated. The reason why it's called CLM is because for a pile soil combination, you develop a characteristic load and a characteristic moment. Now, mind you, the characteristic load and the characteristic moment are not the real moments in the pile. In fact, they're several orders of magnitude greater than that. What they are, however, is expressions of the response of them. How much moment would you get if you apply certain loads to the pile? So that's a 12-inch square concrete pile, restrained head. And when I say restrained, I mean fixed head. Either fixed or restrained heads are the same terminology. 60 foot long, 12 inches square, and the F prime of the C is 6,000 psi, which the shear load is 20 kips, and the soil is a sand. It's 36 degrees and 120 PCF, and the groundwater table at a depth of 40 feet. Find the lateral deflection of the pile top and the maximum moment at the pile top. If you have a free, free head, let me go back, just as a matter of clarification. If you have a free head and you have just a lateral load, you will have a moment, and you, of course, will have shear along the pile. If you have this, you will likewise be able to rotate the head and induce moments down the pile. If you have a fixed head, you don't have this induced moment. What you have is the fixity of the head. The head has to stay perfectly vertical, and the head essentially induces its own moments based upon that. So that's the key difference between a fixed head and a restrained head, and a free head. The example now, let me back up. I've gotten a little bit ahead of myself. This is a screenshot of the results, of the input. Force kips, length in inches. Make sure that whatever units you use are consistent. In other words, if you use, I would suggest to use kips and inches for problems in US units. The thing that trips many students up about this is this. If you have inches, then the gamma has to be in inches, and frequently that doesn't happen. You see that the figure is 6.94 times 10 to the minus 5 kips per cubic inch is a pretty low number, but it's equivalent to the 120 PCF. If you have a round pile, CLM2 will compute it for you. If you leave I believe if you leave I at 0, then it automatically assumes that it's a diameter of 12 inches. And then down here is the modulus elasticity of the pile, which is 4,400 KSF, and the length of the pile, which is also in inches. In other words, if you pick inches for one, you got to carry it through the whole thing. So that's a little bit of a trout in the milk. So you got to be careful with the way you put your units in with this spreadsheet. It does not have the, for example, it doesn't tell you, oh, I could put, you know, my length in feet, which would make sense, my unit weight in, you know, pounds per square cubic foot or kips per cubic foot, and then turn around and say, oh, by the way, the pile dimensions are in inches. It won't let you do that. You have to do, if you use inches for one unit, and you have to make sure that everything is right. Once you do that, though, and you pick, now the spreadsheet itself has several results, and I would suggest before you start playing with it that you look at the little document that came with it. You'll quickly see that you've got for fixed head and free head and combined moment and shear force for free heads. There's all kinds of, I think those are the three combinations the spreadsheet will analyze. This is the fixed head part, and it'll give you all these tables. Make sure you pick the right one when you actually pick the solution. Now, putting in the kips per pile, lateral loading is kind of like settlement. You put in your ultimate objective is to put in a figure for your loads, and then it will give you the deflection. And it allows you to put in any number. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different loads. I only ask you for one load. All you have to do is pick one of those, substitute the whatever loads are over here, and then you read across. In this case, I picked 20 since it's one of the ones that was given, and it gives you a YP, or gives you a maximum moment of 78.5 inch kips and a YP, which is the deflection at the pile head, of 0.183 inches. That's pretty much it. The only thing you have to avoid is misreading the spreadsheet. With Tanwave, it's even simpler. You still have to pick fixed or free head, and you still and Tanwave only analyzes one moment or shear or combination thereof at a time, only one case at a time, and that has to be put in the early stages of input. You have to put the soil parameters in and all that, but you have to. We had to, for this particular case, I had to modify the input a little bit, but I still will get out. And actually, Tanwave shows you a lot of fun things, such as the mile moment of inertia, the section modulus, the solid circle moment of inertia, which is important for the way CLM operates, moment inertia ratio and all that. It also shows you the characteristic load and moment, which you see are very large compared to the actual moments that you're doing and loads that you're doing. And then it finally computes the maximum moment to the pile head load. It's a little different because basically Tanwave doesn't allow you to monkey around with the material properties of the pile. So it's a little different in Tanwave than it is here, but the results are pretty close. It's a fairly straightforward calculation. How do I deal with lateral? Well, how do I verify it, and how would I increase it? Well, obviously, they're full-scale lateral load tests, just like they are, and we'll talk about the axial test mostly when we get to that subject. They can also be used, and they were certainly used by Lyman, Reese, and Mike O'Neill to calculate P-wife curves, although they used a little more instrumentation than that. The model lateral load test. One of the great holy grails of this business has always been model testing. The ability, those of you who had me in fluid mechanics laboratory, we talked about dynamic similarity and wind tunnel testing and that kind of thing. And geotechs have always dreamed of the day when they could run scale model test and get away with it. Well, they haven't. There are many problems associated with model testing, and as a result, and then there's the centrifuge testing, and I think Verroit spent some time on how that works. They've tried a lot of things. So far, model testing is just, even with all the years they've been messing around with it, model tests are used in research fairly extensively, but as far as actually use them to extrapolate field conditions, they're still not ready for prime time. So, and lateral stat dynamic test only uses an impact. In other words, if you want to, and you'll see why here in a little bit when we get to that, how they work. I think the technology is improving on that too. Enhancement, there's all kinds of ways to do it. You can put fins on the pile. You can put berm to back it up, sheet piles. There are a number of ways of enhancing the lateral load capability of a pile. Normally, and of course, one thing you can do, obviously, is make it bigger. And particularly in seismic work, that's the way we do it. So with that finishes our session on lateral loading. Thanks for watching, and God bless.